Caillou sets up, let me go ahead and introduce him. He is the head of Media Analytics Department at NEC Laboratories, Amerika. Before joining NEC, he was a senior research scientist at Siemens Corporate Technology. His research interests are learning from relations, collaborative filtering, multitask learning, computer vision, image classification, deep learning, and sparse coding. And I should note that he led the first place team in the ImageNet Large-Scale Visual Recognition Challenge. And with that, I look forward to hearing his talk.
So hello, everyone. Today, I'm going to talk about image recognition using unsupervised feature learning. So if you look at the title, you can notice there's a big overlap with Andrew's talk because we both believe, actually, a bunch of machine learning guys really believe by learning from data, we can actually obtain very powerful features for image recognition. But there's one part actually I don't want to talk is deep learning because I believe it's hard to be as deep as Andrew did. So, so let me focus on unsupervised feature learning. So in the past 2 years, I worked with a large group of people. Those are my colleagues from NEC Labs. And also we collaborated with professors like Tong Zhang, Thomas Huang, and John Lefty. And by the way, we also have some secret weapons, which are who are our interns. They're very smart and productive. So what we did, I believe, is pretty amazing. So this is one example. So in 2009, this is a PASCAL Visual Object Class Challenge. I think this is probably one of the most prestigious benchmark in computer vision for object recognition. So the task is to classify images to one or multiple of the 20 categories, right? So typically, very often, one image here can be multi-label because containing several different category of objects, right? So in 2009, the task is, okay, given about 8,000 images for training to classify a test set of 6,650 images. So this is the result. And we achieved the #1 positions for 18 of the categories out of total 20 categories, right? Those here for each category will release our performance and the best of performance from other teams. Here's the difference, right? So it's actually pretty encouraging for us because we use learning features, right? We don't, combine all kinds of different features like appearance, shape, texture, those features. We just use hog features on gray images, right? So it's pretty standard, simple feature. But what we really did is learning features from these simple features. And this is a very encouraging result. It shows the potential of learning features from data. Well, you might argue that, okay, we all know human can recognize tens of thousands of objects, right? So the PASCAL challenge is pretty small scale. So we should really, challenge ourselves, to push the boundary and to recognize more and more type of objects. So what's happened last year is pretty amazing. Fei Fei and her colleagues organized this ImageNet large-scale visual recognition challenge. So in this task, we have 1,000 categories of objects to recognize and 1.2 million images for training compared to 20 categories and 10,000 images in PASCAL challenge. So it's much bigger scale of the problem. And we did really well. This shows the result of the of the different teams. And actually, in terms of classification accuracy, we achieved 52% for 1,000 classification. So even from machine learning point of view, this is a pretty high classification accuracy, right? And we all know image classification actually is really, really challenging, right? Much more difficult than text classification. So I think Angel have given quite deep insight about why feature learning is useful. So I think I want to skip this slide. And in particular, I think for image recognition, we also have a strong evidence that biological visual systems actually learn features over, a very long time of evolution, right? So I guess I'm not an expert to talk too much details about this biological system, but I just want to point out the discovery of the visual processing architecture in the primary V1 layer, namely this complex cells and simple cells. Those kind of behaviors actually inspired computer vision researchers develop very powerful visual recognition systems, right? So, for example, this is convolution neural networks, right? So here's the input image, right? Then you apply some nonlinear filter, right, to convolute the input data, and then at different locations, then you get the response map, right? Then to further handle this local invariance, right? So we do like pooling. So for example, average pooling, right? Pull a local response together to get a single response, right? Again, you get a smaller, feature map, and then again on top of that, you apply convolutional filter again, and then pooling again. So you can repeat this process several times, and in the end, put it into a classifier, right? So this is basically the architecture of a convolutional neural network. So you can see here the convolutional filtering, the filter step simulates the behavior of the so-called simple cells, right? And the pooling step simulates the processing of the complex cells, right? I think what's amazing here is this convolutional neural network actually learned the whole structure simultaneously. That means unlike many other vision models, which kind of first, handcraft or whatever to get some image features, and then put into SVM or boosting to get the final outcome. And this model actually learns the whole thing from the pixel level, right? So it's achieved the state-of-the-art performance on a number of different tasks. For example, one thing is digit recognition. And also, I believe for face recognition, this is also one of the best models. So it turns out actually this model probably was developed like more than 20 years ago, right? And recently, people, this is a very popular thing in computer vision community, especially for scene recognition and object recognition, which is so-called bag of visual words model. And in particular, it's combined with spatial pyramid matching to handle the spatial structure. It's achieved really state-of-the-art performance on a bunch of benchmarks. For example, Caltech 101 and PASCAL object recognition, and also like track weight evaluation. But if you look at actually the details of this model, it still follows pretty much the same architecture. For example, here, the first layer, you use local gradient, apply everywhere across the image, and then you do this kind of pooling. So by this way, you obtain sort of dense shift feature or dense hog feature. And on top of that, you apply vector quantization coding, and then apply average pooling. That's the way you get the histogram, right? In the end, you apply linear SVM. So you can see the structure is pretty similar, but the first 2 layers are handcrafted, right? And this VQ coding layer is somewhat like learning because it's learning the vector quantization. You have to apply k-means to the large pool of unlabeled image patches. So this is unsupervised learning, right? So I think our observations on this model is probably there are several ways to start from here to improve this model. So one thing is first this nonlinear SVM is not scalable, right? Even though it's produce very impressive performance, but we all know in computer vision, really, if we want to solve the problem, we have to use a lot of training data, right? So for nonlinear SVM, you cannot, probably it's non-trivial to handle, for example, over 10,000 of training examples. The second one is the VQ vector quantization coding might be too discrete, right? Might be too coarse, not fine enough, right? Because we know the sensory data structure is continuous, right? So probably we need a better coding methods. Then the next one is average pooling, right? So probably average pooling is suboptimal. Actually, I think many researchers observed this. And using something like, for example, max pooling, you can achieve a much better performance, right? So we also need to investigate how to develop, what's the principles to develop better pooling methods, right? The last question is, why don't we learn the whole thing together, right? Instead of fixing the initial 2 layers fixed, right? So this pretty much motivate our work. So our work is pretty much, let's say, let's don't try to do anything too fancy. Let's accept that this kind of architecture is the thing we want to stay with. And then let's, based on these observations, can we do something better, right? So the first thing what we did is replace the nonlinear SVM by simple linear classifier. Then the question is how to computationally train a linear classifier with millions or hundreds of millions or even billions of training examples, right? So we developed stochastic training, to handle this problem. And the second one is the coding part. So how to develop a better coding methods from unlabeled data, right? And the key question we want to ask here is, how do we know? Learning from unlabeled data actually can help you to achieve supervised learning tasks, right? Then the third one is pooling, to develop better pooling methods. The last one is deep learning. That means learning the whole thing together, multiple layers, all the filters together. I think in this talk, I will focus on only 2 parts. The first is nonlinear coding via unsupervised learning. So I think if I have some time, then I will talk a bit more on the pooling side. So here's the notation. This is the input image. Then if we extract the features in the local patches everywhere, then what we get is so-called dense local features. So in this case, each image is represented as a bag of feature vectors, right? In the case of if the feature is safety feature, then it's 128-dimensional feature vector. Then we perform nonlinear mapping to map the features into a new space, right? So this is a nonlinear coding. And typically, the new space, the dimensionality is much higher. And the endable is some representation, not just the high dimensional, but also highly sparse, right? Next, we perform linear pooling, so which is a weighted average of the nonlinear codes together. In the end, we perform linear SVM or any linear classifier. So if we look at this this whole structure and look at this classifier, So this is a linear model applied on the pooled codes. So because this is summation, then you can move the linear operator into the inside of the summation. So then this is a function on the images. This is a classifier on image level. And this is a function on local patches, right? So in this framework, an interesting insight is, so learning a classifier on the level of images actually is closely connected to learn some nonlinear function on local patches. Right? So here's a very high-level idea about learning nonlinear features on the local patches, right? So suppose this is the distribution of the local patches, right? And here's the unknown nonlinear function on local patches, right? So we don't know this nonlinear function. This is something what we want to learn. So the assumption here is the image patches X follow a nonlinear manifold structure, and the target function is smooth on its manifold. So that's our assumption, right? I think this is the key assumption to connect unsupervised learning to supervised learning, right? So that means by learning this interesting structure of unlabeled data, so we can get some information about the target function, right? And that information actually can help us to learn the classifier, okay? So the coding step is to learn a nonlinear mapping from the input data to a high-dimensional space, right? Typically, this is high-dimensional and sparse, right? And then the way to learn such a nonlinear function is to actually put a linear function on this nonlinear mapping, right? Because the mapping is nonlinear, then the linear function here actually is a nonlinear function on the original input, okay? It's clear? Yes. So here's one idea we developed, which is called local coordinate coding. So the intuition is the following. Suppose this is the input data, right? We don't know this nonlinear function, right? And then we want to figure out what's the function value, at this particular location, right? So what we do is, okay, let's say we have a set of bases, right? By whatever method, we have this basis, and then we find some local bases, right? To linearly encode this data point, right? Those are linear coefficients. So we know this target function is nonlinear, but it's reasonable to assume it's locally linear, okay? And if it's locally linear, then what we get is here in the local region, right? So this function value at this location can be represented as a linear combination of the function values on those activated bases, because those bases is also in the local neighborhood, right? So based on the local linear assumption, you have this approximation, right? So this is the way how we interpret this target function value. This is kind of high-level intuition. How do we use the coding methods to learn the nonlinear function? So the procedure is like the following. First, we learn the dictionary from unlabeled data, right? Those are the basis sort of element in a dictionary, right? And the second step is to use the dictionary to encode the data point. So the way we do is, okay, for each data point to be encoded, we find the neighborhood to activate the neighboring bases, right? And we get a set of coefficients, right? Typically, this coefficients is highly sparse, right? So because each data point only activate a small number of neighboring bases, right? That means all the coefficients, most of them are zero, right? Only a small number of bases, non-zero. So this is somehow connected to the sparse coding idea. Then the next step is to estimate the parameters, because based on the local linear assumption, we have this approximation, namely each data point, the function value on each test point can be represented as a linear form, right? Those are linear coefficients of the coding, and those are kind of fixed number of parameters, which corresponding to the function values on the location of the basis, right? So here it turns out those parameters are global linear weights to be learned. So this is pretty interesting because somehow we turn a nonlinear learning problem into kind of simply estimating a linear function, right? So estimating some linear parameters. So we can say something about this function approximation performance. So this is the approximation to the function value at this location, right? It turns out this approximation error is upper bounded by a kind of unsupervised learning objective term, right? Which is the coding error, right? So how close you encode the data point, right? Plus one additional term, which is this is sort of like L1 regularization on the coefficients, right? To encourage sparsity, right? But this is weighted by the distance term, which is the distance between the encoded data point and the basis, right? So if you look at this, if we minimize this upper bound, right, that's actually will push down the function approximation error. But something good is about this term encourage local kind of local bases are tending to be picked up, right? So the key message here is a good coding scheme should be have a small coding error and also be sufficiently local. So based on this principle, we can develop very simple algorithm. So let's say we use dictionary learning, like k-means or hierarchical k-means, to learn a dictionary, right? So then to encode a data point, let's first ensure locality. That means let's pick up neighboring bases, right? So that's somehow similar to vector quantization. But in VQ, you pick up only one basis. Here we pick up multiple bases, right? In the second step, we ensure low coding error. That means we solve this minimization problem with the constraint, right? Then we get the code. So we apply these methods on, for example, here is Caltech 101 and Caltech 256. So on Caltech 101, it's pretty much comparable with state-of-the-art methods using sparse coding on top of a safety feature, right? And on Caltech 256, it's much better, right? You can see here, performance. So the next is another method, pretty much follow the similar idea of exploring the data geometry, right? So this is so-called super vector coding. So it's let's say we want to figure out what's the function value at this location, right? The same as before. So what we do is find the nearest one basis, right? And so one idea is so let's say let's use the function value at this particular location, right, as the approximation of the target function value, right? And if we do this for all the data points, so what we get is something like a piecewise local constant approximation of a nonlinear smooth function, right? Actually, this is pretty much explains how the vector quantization for backwards representation, right, does. Let's say if we can do something better. So again, we want to figure out the function value of this location, and then let's find the nearest basis. Then let's pick up the nearest basis here. So instead of doing zero order approximation, maybe we can explore the structure, a high order structure. Let's say the first order, which is the local tangent, right? So if we do this for all the data points, what we get is a very simple piecewise linear, local linear approximation, right? So we can also look at, so how about the function approximation error, right? So this error is upbounded by simply the vector quantization error, right? That means that's very nice, right? That means we can simply apply VQ to learn the basis, and then just do a little bit twist on top of VQ, then we can get better performance, right? So here's the local tangent term at the location of the basis. So the function approximation can be represented as linear form. So this is the supervector code of data, and those are unknown parameters to be estimated, right? So I think here is a summary of the three coding methods I mentioned. The first one is the popular vector quantization coding. Second one is local coordinate coding. The third one is the supervector coding. So they all lead to kind of a high-dimensional, sparse, and localized coding schemes. And by learning from the unlabeled data, they all explore the geometry structure of data, right? But the new coding methods are more suitable. They explore finer structure of data, and they are all suitable for linear classifiers, right? So their implementations are pretty straightforward. So I have how many minutes do I have? 10. Okay, good. Okay, so in the next, I'm going to talk about, so since we have this nonlinear coding, right, how do we do pooling, right? I think pooling stuff is pretty much a kind of unexplored area. I think people have been, especially in the feature learning community, people have intensively worked on how to learn nonlinear features from data. But pooling step is pretty much in a kind of ad hoc stage, right? I think there's only one work done by Elaine and LeCun last year, ICML, to analyze, theoretically analyze the so-called max pooling, which is pretty much state-of-art methods for the pooling stage, right? But I think this deserves more higher level of interest for further investigation. So let's look at how do we represent the images by local features, okay? So for each image, we extract a bunch of local features at different locations, right? In that sense, each image is represented as a set of features, which is a feature set, right? A feature set is an empirical distribution, right? So that means each image is an empirical distribution like this, right? So one idea to perform image classification, right, is kind of to embed the empirical distribution into a feature space, right? Let's say a Hilbert space, right? And in that space, we do linear classifier, right? This is pretty much like the kernel trick, okay? So let's say this is the embedding of the distribution, right? I think one embedding, people have started this problem. Let's say this work done by Smaller and his colleagues. They consider a embedding in such a very simple form, right? Simply it's average of the nonlinear mapping of the local features, right? So this is pretty much exactly the average pooling, right? There's some problem about this average pooling. I think fundamentally one issue is in this embedding, the kind of norm of the embedding is not properly normalized. It could be unbounded. So It seems to be a mathematical problem, but it's actually also an issue in practice. That means in the image, if some features, some patterns, kind of like noise or whatever, right, repeated and occurring too often, then these components will dominate, the representation of the image data, right? So this is kind of in an intuition level why this simple average pooling is not good. And empirically, this has been observed by many computer vision researchers, right? Max pooling is much better, way better than average pooling, okay? And then let's look at another way of defining a kernel between distributions. This is so-called the Bhattacharyya kernel, which is pretty simple form, right? This is the integration of this, this is the square root of the two densities, right? You take the integration. Right. This is very well behaved in the sense that the norm of this embedding is pretty normalized, right? So its two norm is simply one, right? But one problem of this Bhattacharyya kernel between two distributions is the following. Here is a simple example, right? Suppose you have two distributions, like two peaks, right? Somehow, if you apply this kernel in this case or another case, right, pretty much you get a similar result because this kernel ignore the structure of data, right? If these two peaks are close or far away, this kernel is insensitive, right? Let's say if you have a vector quantization, right, you end up with for each image. In the extremely simple case, each image you end up with one beam, right? So if two images and the two beams are from two images, actually they are very close in the feature space, right? And this Bhattacharyya kernel will treat these two images totally different, right? Somehow ignore the distance, the structure of the data. So then we introduce a smoothing term. So here is the new kernel function we defined between two distributions, right? So what we have here is a nonlinear kernel between on the feature space, right? It doesn't have the problem of the previous Bhattacharyya kernel because of this smoothing term. Actually, it's incorporated the smooth structure of data, right? But however, this definition requires to know the density, which is impossible, right? So then we introduce another formulation, which requiring only a rough estimation of the two densities, which is the P tilde and the Q tilde here. So this formulation induces a new feature representation, which is this formulation. Let me, yes. So this is if we apply these methods into an empirical distribution, so what you get is the following. So this is the empirical distribution, right? The embedding of this empirical distribution is average, but it's weighted average of the nonlinear mapping of the features, right? Here's the weights, right? The weights is based on an estimation of the density, right? So interesting thing here is a nice property here is actually this density estimator doesn't have to be very accurate, right? So as long as the ratio between the estimator of the density and the true density, right, is bounded from above and below, and if the estimator itself converge to a limit, right, so mathematically it will be well behaved. It will achieve desired properties. And we have done actually extensive experiments showed that these new methods perform much better than average pooling. And in most of the cases, it's like equally well or even better than max pooling, right? So let me tell you in which cases this is better than max pooling. Actually, max pooling implicitly assumes the coding is non-negative, right? So it kind of picking up the most prominent response, right? So what about, if we want to just use an arbitrary coding method, just want to explore the geometry structure of data, right? So the coding doesn't have to be non-active, right? In that case, sparse coding will fail, right? And in this case, this new pooling methods will be much better. Yeah. So here I would conclude my talk. So we have developed a series of feature learning methods. We are learning from unlabeled data, and they achieved state-of-art performance on several benchmarks, right? Actually, I have a few demos if I have time, or maybe we can show the demo offline. I'm done, basically. Okay, let me finish the conclusion. Yes, and actually this is the last second slide. I have one more slide. So, and we proposed a new pooling method. It shows very interesting theoretical properties, but also empirically showed better result than average pooling. And for sparse coding or local coordinate coding type of methods, it's the same level as max pooling. But for super vector type of codings, it's way better than max pooling. There's a bunch of interesting directions I think we would like to explore further. So one thing is definitely deep learning, So why don't we learn the whole thing, multiple layers of nonlinear feature transformation, together, right? I think Andrew has given a very excellent coverage on that topic. This is something we are also working on. And the second is definitely interesting is faster methods, for feature extraction, right? Because we have to think about how do we handle, extracted, once the learning is done, the feature learning is done, how do we use the learned model to extract image features, for example, in a level of like 50 millisecond, right? So this is still very challenging. The third thing I think is probably the most interesting to myself is learning powerful features from the richer structure of data. For example, from the video, I think Andrew also mentioned, from the temporal consistency assumption, to explore the kind of temporal consistency, but also to learn kind of invariant features. For example, outplane rotation of the objects. Right? So those are the papers we published over the last 2 years, and thank you very much.